On December 27th, 2004, at exactly 9:30 in the evening, Eastern Standard Time, something strange happened to the Earth. Satellites went blind. Sensitive instruments designed to peer into the deepest reaches of space suddenly overloaded and shut down. The Swift satellite, built specifically to detect gamma rays from the most violent explosions in the universe, was so overwhelmed that its detectors completely saturated. The RESI spacecraft, which monitors solar flares, recorded signals it was never designed to handle. The Pioneer Venus orbiter, drifting through the solar system, was flooded with radiation. Even submarines deep beneath the ocean briefly lost their low-frequency communication systems as the upper atmosphere itself contorted and shifted. Something had reached across 50,000 light-years of empty space and touched the Earth, not gently, not subtly, but with enough power to physically compress our planet's magnetic field, to temporarily ionize the upper atmosphere, and to deliver more energy to Earth in 0.2 of a second than a powerful solar flare. The source was an object no bigger than a city, and it had just demonstrated why astrophysicists consider it to be the scariest thing in the known universe. This is the story of the Magnetar. To understand what happened on that December night and why it should concern anyone who gazes up at the stars, we need to begin with death, specifically the death of massive stars. When a star significantly larger than our Sun exhausts its nuclear fuel, something catastrophic happens. For millions or even billions of years, that star has existed in a delicate balance. The crushing force of gravity, trying to collapse the star into itself, has been held at bay by the outward pressure of nuclear fusion at its core. Hydrogen fuses into helium. Helium fuses into carbon. Carbon into oxygen. Oxygen into silicon. And finally, in the last desperate moments of the star's life, silicon fuses into iron. And here the balance breaks. Iron is the endpoint. It cannot fuse into heavier elements without consuming more energy than it releases. The nuclear furnace at the heart of the star goes dark. And in that instant, gravity wins. What happens next occurs in less than a second. The core collapses. Material that was spread across a volume the size of Earth compresses down to something just 20 kilometers across. Imagine taking every car in the United States and crushing them all into a single sugar cube. Now do it again, and again, and again. That approaches but does not quite capture the density we are talking about. The collapsing core rebounds off itself, sending a shockwave racing outward through the star's outer layers. This is a supernova, one of the most energetic events in the universe. The explosion outshines entire galaxies. It scatters heavy elements forged in the star's final moments across light years of space. And at the center of this cosmic catastrophe, something survives, a neutron star. The matter that falls back after the supernova is so compressed that atoms themselves are crushed. Electrons are forced into protons, forming neutrons. The entire mass of the core becomes a ball of neutrons packed together as tightly as an atomic nucleus. The density is almost incomprehensible. A single teaspoon of neutron star material would weigh somewhere between 1 billion and 10 billion tons, depending on which estimate you use. That is roughly the mass of Mount Everest, compressed into a space that could sit on your kitchen counter. The surface gravity of a neutron star is about 200 billion times stronger than Earth's. If you somehow found yourself on the surface and dropped a pen, it would hit the ground at a significant fraction of the speed of light. Not that you would notice, because you would already be dead. Your body stretched into a thin stream of atoms by the tidal forces long before you reach the surface. Neutron stars are, by any reasonable measure, among the most extreme objects in existence, but they are not the most extreme. In 1979, something puzzling happened. Soviet space probes Venera 11 and 12, orbiting the Sun on their way back from Venus, were struck by an intense blast of gamma radiation. The readings jumped from a normal 100 counts per second to over 200,000 counts per second in a fraction of a millisecond. 11 seconds later, the NASA probe Helios 2 was hit, then Pioneer Venus, then the Vela satellites orbiting Earth, then the Einstein Observatory. The wave washed across the entire inner solar system. By triangulating the arrival times at different spacecraft, scientists pinpointed the source, a supernova remnant called N49 in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, some 165,000 light-years away. The event was unlike anything astronomers had seen before. It had a hard spectrum of gamma rays, characteristic of extremely violent processes. But it also had a pulsating tail, with brightness oscillating every 8 seconds for several minutes. This periodicity pointed directly at a rotating neutron star, but the energy involved was staggering. The initial spike released more power than any gamma ray burst ever recorded at the time, and the pulsating tail suggested something was sitting on the surface of that neutron star, rotating with it, glowing with unimaginable intensity. Scientists were baffled. The event did not fit neatly into any existing category. The March 5th, 1979 event marked a turning point in our understanding of neutron stars, even though it would take another 2 decades before scientists fully understood what they were seeing. The burst originated from the supernova remnant N49 in the Large Magellanic Cloud, a satellite galaxy visible from the southern hemisphere. This association with a young supernova remnant immediately suggested the source was a neutron star, the compressed core left behind when a massive star explodes. But the sheer power of the event challenged existing theories. In the initial spike, which lasted less than a second, the source released energy at a rate of 10 to the 44th ergs per second. To put that in perspective, the Sun's total luminosity is about 4 times 10 to the 33rd ergs per second. The March 5th burst, at its peak, was emitting energy at a rate roughly 10 billion times the Sun's entire output, and it was doing this from an object perhaps 20 kilometers across. The pulsating tail that followed provided crucial information. The 8-second period indicated a rotation rate consistent with a neutron star, but the persistence of those pulses, continuing for over 3 minutes, suggested something was trapped on or near the surface of the star, rotating with it and glowing intensely. Scientists proposed various explanations. Some suggested the burst resulted from material falling onto a neutron star from an accretion disk. Others proposed collisions with asteroids or comets. Still others suggested some exotic particle physics process. None of these explanations quite fit the data. The event remained an anomaly, filed away as a curious outlier while scientists continued observing the sky for more examples. They would not have to wait long. Throughout the 1980s, more strange bursts were detected. They came from a handful of specific locations in the sky, repeating at irregular intervals. Unlike ordinary gamma-ray bursts, which are one-time events, these sources kept flaring up. They were dubbed soft gamma repeaters, or SGRs, for their relatively low-energy gamma-ray emission. But what were they? What could produce such intense, repeated bursts of high-energy radiation? In 1992, two theoretical astrophysicists proposed an answer that most of the scientific community initially dismissed as outlandish. Robert Duncan at the University of Texas at Austin and Christopher Thompson, then at Princeton University, published a paper describing a theoretical object they called a magnetar. They proposed that certain neutron stars could be born with magnetic fields far stronger than any previously imagined, 1,000 times stronger than ordinary neutron stars, which already have magnetic fields 1 trillion times more powerful than Earth's. The numbers they calculated were difficult to comprehend. A typical neutron star has a magnetic field of around 10 to the 12th Gauss. Earth's magnetic field, for comparison, is about half a Gauss. A refrigerator magnet is perhaps 100 Gauss. The strongest magnet ever built by humans reaches about 450,000 Gauss. Duncan and Thompson were proposing objects with magnetic fields of 10 to the 15th Gauss. That is 1 quadrillion times stronger than Earth's magnetic field, a 1 followed by 15 zeros. Most astronomers thought the idea was too extreme to be real. At a scientific conference in 1992, Duncan and Thompson were given just 3 minutes to present their elaborate theory. As late as January 1998, at an American Astronomical Society meeting, the magnetar concept was still being treated as speculative at best, but the universe was about to provide dramatic confirmation. In 1998, astrophysicist Chrissa Cuvelliotto led an international team in a concerted effort to test the magnetar hypothesis. Using American and Japanese X-ray telescopes aboard orbiting satellites, they observed a soft gamma repeater designated SGR 1900 plus 14. What they found matched the predictions of Duncan and Thompson almost exactly. The neutron star was emitting X-ray pulses even when it was not bursting, and the rate of those pulses was slowing down at precisely the speed predicted for a magnetar whose intense magnetic field was acting as a brake on its rotation. On August 27th, 1998, the same source erupted in a massive flare. The radiation was intense enough to force the near-Shoemaker spacecraft to shut down to prevent damage. Instruments on Beppo sacks, wind, and RXTE were saturated. This event, combined with the timing measurements, clinched the case. Magnetars were real. The August 1998 event from SGR 1900 plus 14 deserves its own examination. This magnetar, located about 20,000 light-years away in the constellation Aquila, had been relatively quiet for years, with significant bursts recorded only in 1979 and 1993. Then it woke up. Beginning in May 1998, the magnetar entered an active phase, producing numerous smaller bursts. But on August 27th, it unleashed something extraordinary. The gamma-ray and X-ray emission was so intense that the near-Shoemaker spacecraft, then approaching the asteroid Eros, had to shut down to prevent permanent damage to its instruments. The Beppo satellite was saturated. Wind and RXTE recorded off-scale readings. Unlike the March 1979 event, which came and went with little follow-up capability, scientists were now better prepared to study such events. Within hours, radio telescopes around the world turned toward the source. They detected an expanding nebula of radio-emitting particles blown off the Magnetars surface during the flare. In May 2008, NASA's Spitzer Space Telescope discovered something remarkable: a ring of material surrounding SGR 1900 plus 14. Analysis suggested this ring had formed during the 1998 giant flare, debris from the explosion that had since spread into a shell around the Neutron star. This discovery provided direct evidence of the violence these events produce. The magnetar had not merely released radiation, it had physically ejected material into space, creating a visible structure that persists to this day. The sequence of giant flares in 1979, 1998, and 2004 established a pattern. These events are rare but recurring. They come from objects with extreme magnetic fields, and they release more energy in fractions of a second than most astrophysical processes produce in years. But the true demonstration of their terrifying power was still 6 years away. SGR 1806-20 sits on the far side of our galaxy, roughly 50,000 light-years from Earth, hidden behind dense interstellar clouds in the direction of the constellation Sagittarius. It was discovered in 1979 and identified as a soft gamma repeater. It has a diameter of no more than 20 kilometers. It rotates once every 7.5 seconds. As of today, it holds the record for the most highly magnetized object ever observed. Its magnetic field exceeds 10 to the 15th Gauss. To put that in perspective, if SGR 1806-20 were placed at the distance of the Moon, roughly 384,000 kilometers away, its magnetic field would wipe the information from every credit card on Earth. The magnetic strips that store your banking data, the hard drives in your computers, the digital storage systems that run modern civilization, all of them would be erased from nearly half a light second away. But that is just a party trick compared to what this object is capable of. 42,000 years before December 27th, 2004, something happened on the surface of SGR 1806-20. The star's crust, made of the strongest material known in the universe, cracked, a starquake. To understand what this means, you need to understand the peculiar structure of a magnetar. The interior is a liquid-like soup of neutrons, protons, and electrons, so dense that a cubic centimeter would weigh 100 million tons. This interior is a superb conductor of electricity. The magnetic field threads through it, coupling the core to the surface. The outer layer, however, is different. It is a crust, perhaps a kilometer thick, made mostly of iron compressed to nuclear densities. This crust is 10 billion times stronger than steel. It is harder than anything that exists on Earth by a factor that defies analogy. But even this incredible material has limits. In a magnetar, the magnetic field is so powerful that it exerts enormous stresses on the crust. The field lines loop through the star's interior, twisting and winding as the liquid core moves. This creates pressure that builds over time. The crust strains, it deforms, and eventually it breaks. When the crust of SGR 1806-20 cracked, the starquake that resulted measured approximately magnitude 32 on a logarithmic scale, equivalent to the Richter scale we use for earthquakes. The largest earthquake ever recorded on Earth was about magnitude 9. The Richter scale is logarithmic, meaning each increment represents roughly 32 times more energy. A magnitude 32 starquake releases more energy than is possible to meaningfully compare to any terrestrial phenomenon. The crack in the crust, probably just a few centimeters deep, triggered a catastrophic release of magnetic energy. The magnetic field lines, suddenly freed from their previous configuration, snapped and reconnected. The energy stored in those field lines was converted instantly into radiation. In 1/10 of a second, SGR 1806-20 released 10 to the 40th joules of energy. That is more energy than the Sun releases in 150,000 years, compressed into a burst of gamma rays barely longer than a human heartbeat. The radiation raced outward at the speed of light. 42,000 years later, it arrived at Earth. NASA described what happened as the brightest event from outside the solar system ever observed in the history of astronomy. The initial spike of gamma rays outshone the full moon by a factor of 2. It was brighter than any solar flare. It was brighter than any supernova observed since Johannes Kepler watched one light up the sky in 1604. The gamma rays struck Earth's ionosphere, the layer of the atmosphere beginning about 50 kilometers up, where gas is so thin that atoms become ionized. The radiation created additional ionization, briefly expanding the ionosphere's extent. This disruption altered the shape of the boundary layer that certain radio communications depend on, including some military submarine communication systems. The European Space Agency's cluster and double-star satellites, designed to study Earth's magnetosphere, recorded the entire event. Analysis of their data provided the first observational evidence that the Magnetars crust had actually cracked, confirming the starquake theory. The scientists estimated the fracture size at approximately 5 kilometers. A significant crack, considering the star itself, is only about 20 kilometers across. Brian Gensler of the Harvard-Smithsonian Center for Astrophysics noted that only the Sun, and perhaps a handful of spectacular comets, have ever delivered more total energy to Earth than that 0.2 of a second burst from SGR 1806-20. He also pointed out something sobering. Had this event occurred within 10 light-years of Earth, rather than 50,000 light-years away, it would have severely damaged our atmosphere. The gamma rays would have stripped away the ozone layer, exposing the surface to lethal levels of ultraviolet radiation from the Sun. The effect would have been similar to a 12-kiloton nuclear explosion at an altitude of 7.5 kilometers, but across the entire planet simultaneously. Mass extinction would have been likely. This brings us to a question that should concern anyone living on this particular pale blue dot. Are there magnetars close enough to threaten Earth? The closest known magnetar is XTEJ 1810-197, located approximately 8,000 light-years away. Another nearby magnetar, designated 1 E1048.1-5937, sits about 9,000 light-years distant in the constellation Carina. These distances sound vast, and they are. Light traveling at 300,000 kilometers per second takes 8,000 years to cover the distance to the nearest known magnetar. Any flare from these objects would have to be astronomically more powerful than the 2004 event to cause significant harm at Earth. But there is a catch. Estimates suggest that only about 30 magnetars have been confirmed in our galaxy. Given their short active lifetimes of roughly 10,000 years before their magnetic fields decay, and the fact that approximately 1 in 10 supernovae may produce a magnetar. Astronomers estimate there could be 30 million inactive magnetars scattered throughout the Milky Way. These are objects that have exhausted their magnetic fury and faded into obscurity, no longer visible as the dramatic gamma-ray sources we can detect. What this means is that we do not know where all the magnetars are. We detect them when they flare, when they are young and active, when they are drawing attention to themselves across thousands of light years. But we cannot easily see the old, quiet ones or the young ones that have not yet experienced their first major outburst. The universe may harbor magnetars we have not yet identified, some of which could be closer than we currently realize. But the danger from magnetars is not limited to their giant flares. Consider what would happen if you could somehow approach one of these objects. Not that you would want to, not that any sensible being ever would, but imagine it as a thought experiment. At a distance halfway from here to the moon, the magnetic field would be strong enough to erase every digital storage device on your spacecraft, assuming you had reached that point in a spacecraft, which you would not have, because the radiation environment would have killed you long before. At a distance of about 1,000 kilometers from the magnetar's surface, the magnetic field reaches a threshold where chemistry itself begins to fail. The electron clouds surrounding atoms are distorted by the magnetic force. Hydrogen atoms, normally spherical, are compressed into needle-shaped cylinders 200 times narrower than their normal diameter. The atoms in your body would be stretched into long rods. The chemical bonds that hold your molecules together would become impossible to maintain. You would not merely die. You would be restructured at the atomic level. As described in a 2003 Scientific American article, remarkable things happen within magnetic fields of magnetar strength. X-ray photons readily split in two or merge together. The vacuum itself becomes polarized, behaving like a birefringent crystal that separates light into different polarization states. Matter and radiation interact in ways that only occur in the most extreme conditions predicted by quantum electrodynamics. Victoria Caspi, a professor of physics at McGill University, who has spent her career studying neutron stars and magnetars, described these objects in appropriately dramatic terms. Magnetars are the most magnetic objects known in the universe. Period. Nothing else comes close. A typical refrigerator magnet is to a magnetar, as a candle is to a thermonuclear weapon. The question of how magnetars form remains an active area of research. The leading theory, developed by Duncan and Thompson, involves a dynamo mechanism. When certain massive stars collapse into neutron stars, if the conditions are right, if the initial rotation is fast enough and the temperature profile is correct, a dynamo process kicks in during the first few seconds after formation. Heat and rotational energy are converted into magnetic energy, amplifying the magnetic field from the already enormous values of typical neutron stars to the extreme values seen in magnetars. This process requires the newborn neutron star to rotate extremely rapidly, perhaps spinning once every few milliseconds. The rapid rotation, combined with vigorous convection in the proto-neutron star's interior, drives the dynamo that generates the magnetar's extraordinary field. The conditions required for magnetar formation appear to be quite specific. The progenitor star must be massive enough to produce a neutron star rather than a white dwarf. typically requiring an initial mass of 10 to 25 times the Sun's mass. But it cannot be so massive that the core collapses directly into a black hole. The star must also rotate rapidly. This is crucial because the dynamo mechanism that amplifies the magnetic field depends on differential rotation within the collapsing core. Different layers of the fluid rotating at different speeds create the shearing motions that wind up the magnetic field lines. Interestingly, there is evidence that magnetars form preferentially in binary star systems. In 2014, astronomers discovered a magnetar that appeared to be escaping from our galaxy at high velocity. By tracing its trajectory backward, they determined it had been ejected from a region where binary stars are common. The explanation involves mass transfer between the two stars. When one star in a binary system begins to expand as it ages, it can transfer material to its companion. This material carries angular momentum, spinning up the receiving star. When that star eventually explodes as a supernova, its core may be rotating rapidly enough to trigger magnetar formation. This binary formation channel might explain why magnetars are relatively rare. Not every massive star has a suitable companion. Not every binary interaction leads to the right spin-up. The conditions must align precisely to produce a magnetar rather than an ordinary neutron star. A study published in 2020 by researchers at CEA Saclay, the Max Planck Institute for Astrophysics, and the Institut de Physique du Globe de Paris provided new computer simulations supporting this picture. They found that when a neutron star is born rotating at the right speed, a powerful dynamo mechanism can indeed amplify magnetic fields to the levels observed in magnetars. Interestingly, this same mechanism may explain some of the most powerful explosions in the universe. The millisecond magnetar scenario proposes that rapidly rotating, highly magnetized neutron stars can transfer their rotational energy to supernovae, making them far more luminous than they would otherwise be. Some hypernovae and gamma-ray bursts may be powered by newborn magnetars. Speaking of gamma-ray bursts, scientists have wondered whether magnetar flares might have affected Earth in the distant past. In 2004, a team of researchers led by Adrian Mellott at the University of Kansas published a paper exploring whether a gamma-ray burst could have triggered the late Ordovician mass extinction, which occurred approximately 440 million years ago. This was one of the 5 largest mass extinction events in Earth's history, eliminating perhaps 60% of marine genera. The paper noted that a gamma-ray burst within our galaxy could do considerable damage to Earth's biosphere. Rate estimates suggest that a dangerously near burst should occur on average 2 or more times per billion years. A 10-second burst from within a few thousand light years would strip the Earth's atmosphere of half its ozone almost immediately. The resulting increase in ultraviolet radiation reaching the surface would be devastating to surface-dwelling organisms, particularly those in the upper ocean that rely on protection from UV light. Intriguingly, the pattern of extinction during the late Ordovician shows some features consistent with this hypothesis. Planktonic organisms near the ocean surface were harder hit than deep water dwellers. Burrowing species survived better than those living on the seabed surface. These patterns match what would be expected from a sudden increase in surface UV radiation. While the gamma-ray burst hypothesis for the Ordovician extinction remains speculative, it highlights a sobering point. Earth has likely been irradiated by powerful cosmic explosions multiple times over its 4.5 billion year history. Some of these events may have had significant effects on the development of life, and magnetars, with their immense energy releases and their presence scattered throughout our galaxy, are prime candidates for the sources of such cosmic assaults. The universe, it turns out, has equipped certain dead stars with weapons of truly terrifying power. Consider the numbers one more time. A magnetar is 20 kilometers across. It weighs more than the Sun. It rotates once every few seconds. It has a surface gravity 200 billion times Earth's. A teaspoon of its material would weigh billions of tons. Its magnetic field is a quadrillion times stronger than our planet's. And when its crust cracks, when the accumulated magnetic stress finally exceeds the strength of the strongest material in existence, it can release more energy in a fraction of a second than our Sun produces in 100,000 years. That energy, traveling at the speed of light, can ionize atmospheres and disrupt civilizations from halfway across the galaxy. These objects are real. They exist in our galaxy, scattered among the hundreds of billions of stars that make up the Milky Way. One of them reached out and touched Earth just 2 decades ago, reminding us how small and fragile our world is in the cosmic scheme of things. The astrophysicist Phil Plett, who writes extensively about space hazards, put it bluntly when discussing magnetars. He is worried about them. Given what happened in 2004, given that the object responsible was exceptionally powerful, and that even stronger events might be possible, the potential threat deserves attention. The good news is that the nearest known magnetars are thousands of light years away, far enough that even their most powerful flares should not threaten Earth with extinction-level damage. The uncertain news is that we probably have not found all of them. There may be magnetars closer than we know, objects that have not yet announced themselves with a dramatic burst, or old magnetars that have faded below our detection threshold. The concerning news is that there is nothing we could do if a magnetar did flare in our cosmic neighborhood. The radiation travels at the speed of light. There would be no warning. The first sign would be the impact itself, a sudden wash of gamma rays and X-rays flooding over the planet without any possibility of preparation or defense. But perhaps the most remarkable thing about magnetars is not the danger they represent. It is what they tell us about the universe. These objects exist at the boundary of physical possibility. Their magnetic fields approach the theoretical limit where the vacuum itself begins to break down. Their densities approach the threshold beyond which matter collapses into black holes. Their internal physics involves conditions that cannot be replicated in any laboratory on Earth, and yet they are real. They form naturally, emerging from the death throes of massive stars. The universe creates them routinely, perhaps one for every 10 supernovae, scattering them through galaxies like ours by the millions. When we observe a magnetar, when we detect the gamma rays from a starquake that occurred tens of thousands of years ago, we are witnessing matter behaving in ways that stretch our understanding of physics to its limits. We are seeing quantum electrodynamics in action, electrons and photons interacting in magnetic fields so strong that the vacuum itself becomes a participant in the physics. We are watching neutron superfluid and proton superconductor phases of matter, states that exist nowhere else except in the cores of these extraordinary objects. In this sense, magnetars are not just threats. They are laboratories. They are windows into physics we could never otherwise access. They reveal aspects of reality that remain hidden under the gentle conditions that prevail here on Earth. On that December night in 2004, when radiation from SGR 1806-20 swept through the solar system and briefly expanded Earth's ionosphere, something else happened that should give us pause. Earth's magnetic field shifted, not by much, not enough for anyone to notice in daily life, but measurements from satellites before and after the event show that the burst left a permanent imprint on our planet's magnetic configuration. A small object, 20 kilometers across, 50,000 light-years away, reached across the vast emptiness of intergalactic space and permanently altered the magnetic environment of our world. This is the power that exists out there among the stars. This is the scale on which the universe operates. And this is why, when scientists are asked what the scariest thing in the cosmos might be, many of them point not to black holes, not to supernovae, not to gamma-ray bursts, but to the small, dense, impossibly magnetic remnants of dead stars that spin in the darkness and occasionally remind us that we are not alone in the universe. Let us return to that December night in 2004 and examine what scientists learned from the event in more detail. When the gamma rays from SGR 1806-20 arrived at Earth, they did not simply wash over the planet and disappear. They left evidence. They created signatures in our atmosphere and in the instruments designed to study it. Paul Campbell, an amateur astronomer in Edmonton, Alberta, was operating a homemade antenna and receiver setup that evening. He was monitoring the 24.8 kilohertz radio signal from the United States Navy's 250 kilowatt transmitter in Jim Creek, Washington. This was part of the extremely low-frequency communication system used to contact submarines deep underwater. The signal he recorded shows a sharp increase in strength at the exact moment the gamma ray burst arrived. This happened because the gamma rays ionized the lower atmosphere, effectively lowering the reflective layer that bounces these radio signals around the Earth. The change was sudden and unmistakable, a direct physical measurement of a cosmic event that occurred 50,000 light-years away. David Palmer of Los Alamos National Laboratory, who led one of the teams analyzing the SWIFT satellite data, described the event in appropriately dramatic terms. This might be a once-in-a-lifetime event for astronomers, he said, as well as for the neutron star itself. Scientists know of only 2 other giant flares in the past 35 years, and the December 2004 event was 100 times more powerful than either of them. The rarity of these events makes each observation precious. Giant magnetar flares have been recorded on Earth only 3 times, in 1979, 1998, and 2004. The intervals between them are decades. If a pattern exists, we do not yet have enough data points to recognize it. The internal structure of a magnetar deserves closer examination because it is unlike anything else in the universe. Start at the surface. The outer crust of a magnetar is a crystalline lattice of iron nuclei, compressed to densities that would be impossible on Earth. This iron is not like the iron in your blood or in steel bridges. It is iron that has been squeezed until the electrons form a degenerate gas, a state of matter where quantum mechanical effects dominate. The atoms are arranged in a rigid crystal structure, each one held in place by the collective pressure of all the others. This crust is less than a kilometer thick, perhaps a few hundred meters in places. It sits atop a transition zone where the matter becomes increasingly neutron-rich. As you descend through this layer, the composition shifts. Iron nuclei give way to exotic nuclear structures, shapes that physicists call nuclear pasta because of their resemblance to various pasta forms. There are flat sheets of neutrons called lasagna. There are tubes called spaghetti. There are bubbles and blobs with names like gnocchi. These phases of nuclear matter exist nowhere else in the observable universe except inside neutron stars. They represent matter at densities just below nuclear saturation, in the narrow window between solid crust and liquid core. The physics governing these structures is still not fully understood. Below the pasta layer lies the outer core, a sea of superfluid neutrons mixed with superconducting protons and relativistic electrons. This is not an ordinary fluid. It is a quantum mechanical superfluid, meaning it flows without friction. The neutrons are paired into Cooper pairs, just as electrons pair in superconducting metals, but at energy scales billions of times higher. The inner core remains mysterious. At the extreme densities found at the center of a neutron star, perhaps exceeding 10 times the density of an atomic nucleus, even neutrons may break down into their constituent quarks. There could be a soup of up quarks, down quarks, and strange quarks forming what physicists call strange quark matter. Or there could be other exotic phases that current physics cannot fully predict. The point is that a magnetar's interior represents a physics laboratory operating under conditions that no experiment on Earth can replicate. Every observation of a magnetar, every measurement of its behavior, provides data on how matter behaves at the most extreme densities and magnetic field strengths possible outside a black hole. NASA launched the Neutron Star Interior Composition Explorer, or NISA, to the International Space Station in 2017, specifically to probe the physics of neutron stars. This X-ray telescope measures the pulses from rotating neutron stars with unprecedented precision, allowing scientists to constrain theories about what happens inside these objects. Todd Strohmeyer, a NASA astrophysicist and co-investigator on the NISA mission, described the challenge facing scientists trying to understand magnetars. Deep inside these objects, he explained, everything just becomes a soup of neutrons and protons, the basic building blocks of atoms. In fact, the matter may be so dense that these atomic components are being crushed into their fundamental particles, called quarks. Strohmeyer likened the structure to a cosmic candy bar with a gooey center and a hard shell. The magnetar's soupy core may be surrounded by a crust resembling super-hot, dense iron crystal. This crust, he noted, is the strongest material known in the universe, yet it is not quite strong enough to contain the phenomenal power of a bursting starquake. Anna Watts, an astrophysicist at the University of Amsterdam who studies neutron stars and black holes, emphasized how much remains unknown. Scientists still do not know what triggers these bursts. The current theory suggests that similarly to earthquakes, the crust rips as the magnetar's powerful magnetic field moves, but the details remain elusive. Watts and other researchers hope that future observations, particularly of giant flares, will reveal more about the physics at play. If a starquake occurs while NICA is operational, the unprecedented timing precision could reveal details about how the crust fractures and how the magnetic field reconfigures. The challenge is that magnetar flares are unpredictable. Scientists cannot schedule observations for events that happen without warning. They can only keep watching, instruments ready, hoping to catch the next burst when it comes. The relationship between magnetars and the broader population of neutron stars raises interesting questions about stellar evolution. As of the most recent catalogues, approximately 30 confirmed magnetars are known. The McGill Online Magnetar Catalogue maintains a list of these objects along with their observed properties, but 30 is a tiny number compared to the roughly 3,000 radio pulsars that have been discovered. This disparity reflects several factors. Magnetars are visible mainly when they are actively bursting, which they do for only about 10,000 years before their magnetic fields decay. Pulsars, on the other hand, can remain detectable for millions of years as their radio beams sweep past Earth with clockwork regularity. The math suggests a different picture of relative populations. If magnetars are active for 10,000 years and pulsars for 10 million years, and if both form at comparable rates, there should be about 1,000 times more inactive magnetars than active ones. This implies tens of millions of dormant magnetars scattered through our galaxy. Where are they all? The answer is that they have become invisible. Their magnetic fields have decayed below the threshold needed to produce observable bursts. They spin too slowly to be detected as radio pulsars. They glow faintly in X-rays, but not brightly enough to stand out against the background radiation. These ghost magnetars drift through the galaxy, undetectable by current instruments. They are the remnants of violent births, stellar corpses that once shook the cosmos with their fury, but now pass through space in silence. Some researchers have proposed that under certain circumstances, dormant magnetars might reactivate. If the internal magnetic field were to undergo a sudden reconfiguration, perhaps triggered by some instability in the core, the surface field might strengthen again. The magnetar could emerge from its dormant state and begin bursting once more. There is tentative evidence for such behavior. In 2003, scientists discovered a magnetar that had apparently turned on quite recently. Observations from earlier in the year showed only a dim neutron star. Months later, it was producing the characteristic X-ray pulsations and occasional bursts of a full-fledged magnetar. This suggests that the magnetar stage might not be a permanent classification. Neutron stars might enter and exit the magnetar phase multiple times during their existence, depending on the evolution of their internal magnetic fields. The study of magnetars has implications beyond understanding exotic stars. Because the extreme conditions inside magnetars cannot be replicated in Earth-based laboratories, these objects serve as natural physics experiments. They allow scientists to test theories about matter and radiation under conditions that stretch the known laws of physics to their limits. The magnetic fields in magnetars exceed the quantum critical threshold, where the behavior of electrons changes fundamentally. Below this threshold, electrons orbit atomic nuclei in the familiar shells described by quantum mechanics. Above it, the magnetic field constrains electrons to move only along field lines, distorting atoms into elongated shapes and altering the chemistry of matter. This regime of ultra-strong magnetic fields was first explored theoretically in the 1970s, but until magnetars were discovered, it remained an academic curiosity. No object in the universe was known to produce such fields. Now scientists can compare their theoretical predictions against observations of real magnetars, testing and refining their models. Similarly, the gravitational fields of magnetars provide tests of general relativity in the strong field regime. Light escaping from a magnetar's surface must climb out of a gravitational well, so deep that it loses a significant fraction of its energy in the process. This gravitational redshift can be measured, providing data on the neutron star's mass and radius. The combination of extreme gravity and extreme magnetism makes magnetars unique laboratories for testing physics. Nowhere else in the observable universe do these two phenomena combine at such extreme levels. Looking to the future, several developments promise to advance our understanding of magnetars. Gravitational wave detectors like LIGO and Virgo have already revolutionized astronomy by detecting the ripples in spacetime produced by merging black holes and neutron stars. Scientists hope that these instruments might someday detect gravitational waves from magnetar flares. When a magnetar's crust cracks in a starquake, the sudden rearrangement of mass should produce gravitational waves. These waves would be much weaker than those from compact object mergers, but a sufficiently close or powerful event might be detectable. Detecting gravitational waves from a magnetar would provide direct information about the starquake itself, complementing the electromagnetic observations. Scientists could measure how much mass moved, how quickly it rearranged, and how the event propagated through the star. The Square Kilometre Array, a next-generation radio telescope currently under construction, will dramatically increase our ability to detect fast radio bursts. If many of these bursts originate from magnetars, as the 2020 discovery suggests, the Square Kilometre Array should detect them by the thousands, providing statistical data on how magnetars behave across cosmic time. X-ray observatories continue to improve as well. NASA's future missions promise better sensitivity and timing precision than current instruments. Each advance brings scientists closer to understanding the physics inside these extraordinary objects. Perhaps the most remarkable thing about magnetars is not the danger they represent. It is what they tell us about the universe. These objects exist at the boundary of physical possibility. Their magnetic fields approach the theoretical limit where the vacuum itself begins to break down. Their densities approach the threshold beyond which matter collapses into black holes. Their gravitational fields bend space-time so severely that light itself must climb out of a deep well to escape. In a magnetar, we see nature testing the boundaries of what is physically possible. Imagine the magnetic field lines as invisible threads running through and around the star. In a simple magnetic dipole, like a bar magnet, these lines run from one pole to the other, looping through the space around the magnet and back again. A magnetar's field includes this dipole component, but it is far more complex. The field is anchored in the superconducting proton fluid of the outer core. It threads through the crystalline crust, emerging into the magnetosphere that surrounds the star. But the relationship between the interior field and the crust is not passive. The two are coupled. When the field moves, the crust responds. When the crust breaks, the field rearranges. This coupling is what makes magnetars so violent. As the magnetar ages, its rotation slows. The field configuration that was stable at one rotation rate becomes unstable at another. Stresses build in the crust. The magnetic field lines, which want to relax into a lower energy configuration, are held in place by the rigid crust. The system stores energy like a wound spring. When the crust finally cracks, the stored magnetic energy is released explosively. The field lines snap and reconnect, converting magnetic energy directly into radiation. This process is analogous to magnetic reconnection events on the Sun, which drive solar flares, but scaled up to powers that dwarf anything in our solar system by factors of billions. Rosalba Perna, an astrophysicist at the University of Colorado, and Jose Pons at the University of Alicante, have modeled this process in detail. Their simulations track the evolution of magnetic stress in a magnetar's crust over thousands of years, predicting when and how intensely the star will burst. What they found was illuminating. Younger magnetars tend to be more active, bursting more frequently and with higher energies. As magnetars age, their activity decreases, not just because the field is decaying, but because the geometry of the field becomes more stable. The system settles into configurations that can support higher stresses before breaking. But the relationship is not simple. Two magnetars with similar field strengths can have very different activity levels, depending on how their fields are configured. The geometry matters as much as the magnitude. In 2020, astronomers made a discovery that connected magnetars to another cosmic mystery. Fast radio bursts, or FRBs, are exactly what they sound like. Brief flashes of radio waves, lasting just a few milliseconds, originating from sources outside our galaxy. They were first detected in 2007, and they have puzzled scientists ever since. The energy in a single burst can exceed what the Sun produces in a year, yet the source must be incredibly compact to produce such a rapid signal. For years, the leading hypothesis was that FRBs came from magnetars. The extreme magnetic fields and violent outbursts of these objects seem like natural candidates for producing such intense, brief radio emissions. Then, in April 2020, astronomers detected an FRB originating from inside our own Milky Way. They traced it to a known magnetar, SGR 1935 plus 2154. For the first time, a fast radio burst had been definitively linked to a specific object. This discovery transformed our understanding of both phenomena. It confirmed that magnetars can produce FRBs, providing a physical explanation for at least some of these mysterious signals. And it revealed that FRBs are not exclusively extragalactic phenomena. They happen in our own cosmic neighborhood, generated by the same objects that have already demonstrated their ability to affect Earth. Victoria Caspi, who has studied magnetars for decades, noted the significance. Magnetars have become central to understanding some of the most energetic events in the universe. From soft gamma repeaters to anomalous X-ray pulsars to fast radio bursts, these objects keep appearing whenever astronomers encounter unexplained high-energy phenomena. Caspi's own career illustrates the growth of magnetar science. When she began studying neutron stars in the 1990s, magnetars were still considered speculative by many astronomers. Using data from the Rossi X-ray Timing Explorer satellite, she and her colleagues demonstrated that anomalous X-ray pulsars, a class of slowly rotating neutron stars with unusually strong X-ray emission, were in fact magnetars. This discovery effectively doubled the known magnetar population and showed that these objects manifest in multiple ways. Some appear as soft gamma repeaters, producing bursts of gamma rays. Others appear as anomalous X-ray pulsars, steadily emitting X-rays powered by their decaying magnetic fields. The underlying physics is the same, an extremely magnetic neutron star converting magnetic energy into radiation. In 2002, Caspi and her colleagues clinched the connection between these two classes of objects by detecting soft gamma repeater-like bursts from several anomalous X-ray pulsars. The distinction between categories was artificial. They were all magnetars, seen from different angles or at different stages of their evolution. Today, the McGill Online Magnetar Catalogue lists approximately 30 confirmed magnetars, with additional candidates awaiting verification. This number represents only the tip of the iceberg. Given that magnetars are active for only about 10,000 years before their magnetic fields decay, and given the estimated rate of supernova explosions in our galaxy, scientists calculate that millions of inactive magnetars likely populate the Milky Way. These dormant magnetars have exhausted their magnetic fury. Their fields have decayed below the threshold needed to produce observable bursts. They spin quietly in the darkness, indistinguishable from ordinary neutron stars, except for subtle differences that current instruments cannot detect. The study of magnetars has also revealed unexpected connections to some of the most violent explosions in the universe. Gamma ray bursts, the most energetic electromagnetic events since the Big Bang, come in two varieties. Long-duration bursts, lasting more than 2 seconds, are associated with the collapse of massive stars into black holes. Short-duration bursts, lasting less than 2 seconds, were long thought to result from the merger of two neutron stars, or a neutron star and a black hole. But the December 2004 event from SGR 1806-20 complicated this picture. The initial spike of hard gamma rays lasted only about 0.2 of a second. If the same event had occurred in a distant galaxy, millions of light years away, it would have appeared indistinguishable from a short gamma ray burst. This realization had profound implications. It meant that some fraction of the short gamma ray bursts detected from other galaxies might not be neutron star mergers at all. They might be magnetar giant flares, events powerful enough to be visible across cosmological distances. Scientists now estimate that somewhere between 1 and 15% of short gamma ray bursts could be extragalactic magnetar flares rather than merger events. The giant flare from SGR 1806-20, if it had occurred in the Andromeda galaxy, roughly 2.5 million light-years away, would have been detectable by current instruments. This connection between magnetars and gamma-ray bursts extends further. The millisecond magnetar model proposes that some long gamma-ray bursts might be powered not by accretion onto newly formed black holes, but by the magnetic braking of rapidly spinning, highly magnetized neutron stars. In this scenario, when a massive star collapses, it can form either a black hole or a neutron star, depending on its mass. If it forms a rapidly rotating magnetar, the enormous magnetic field extracts rotational energy and channels it into the explosion, making the supernova far more luminous than it would otherwise be. Some of the brightest supernovae ever observed, called superluminous supernovae, may be powered by this mechanism. A newborn magnetar, spinning hundreds of times per second and boasting a magnetic field of 10 to the 15 Gauss, could inject enough energy into a supernova to make it outshine normal supernova by factors of 10 or more. The question of how close a magnetar would need to be to seriously threaten Earth deserves careful consideration. Studies by Mellett and his colleagues estimated that a gamma-ray burst within about 3 parsecs, or roughly 10 light-years, would severely damage Earth's ozone layer. The incoming radiation would trigger atmospheric chemistry that would deplete ozone for years, allowing dangerous ultraviolet radiation from the sun to reach the surface. But not all magnetar flares are created equal. The December 2004 event from SGR 1806-20 was exceptionally powerful, roughly 100 times more energetic than the previous record-holding giant flare. Smaller flares, which occur more frequently, would need to be correspondingly closer to cause the same level of damage. The good news is that giant magnetar flares appear to be rare, perhaps occurring only once every several decades per active magnetar. And the closest known magnetars are thousands of light years away, far beyond the danger zone. But there is uncertainty in these estimates. We do not know how many magnetars exist in the solar neighborhood. We do not know the maximum possible energy of a giant flare. We do not have a complete census of even the active magnetars in our galaxy, let alone the millions of inactive ones that have exhausted their magnetic fury. What we do know is that the universe has demonstrated it can reach out and touch our planet from distances that once seemed safely remote. The December 2004 event was a reminder that cosmic geography is not as protective as we might assume. There is something almost philosophical about magnetars. These objects represent the universe operating at its limits. Their densities approach the theoretical maximum before matter collapses entirely into a black hole. Their magnetic fields approach the theoretical limit where quantum electrodynamic effects become dominant. Their gravitational fields bend space-time so severely that light itself must climb out of a deep well to escape. In a magnetar, we see nature testing the boundaries of what is physically possible. And yet, they are natural objects. They are not engineered or designed. They emerge spontaneously from the death of massive stars, products of the same stellar evolution that scattered the heavy elements necessary for planets and life throughout the cosmos. The same processes that made Earth possible also create magnetars. This is perhaps the deepest lesson these objects teach us. The universe is not especially concerned with our survival. It operates according to physical laws that produce both habitable planets and lethal cosmic hazards with equal indifference. We exist in the narrow band of conditions that happen to be favorable to life, surrounded by phenomena that would destroy us without malice or intention. The magnetar does not care about Earth. It does not know we exist. It spins in the darkness, accumulating stress in its crust. And when that crust breaks, it releases energy that travels at the speed of light in all directions, indifferent to whatever might lie in its path. We are merely fortunate that the geometry of the galaxy has placed us far from any known magnetar, and that the one whose flare reached us in December 2004 was safely distant enough that we experienced only a brief disruption rather than catastrophe. Let us consider what the December 2004 event would have been like from closer range. At 50,000 light years, the flare was bright enough to briefly outshine the full moon in gamma rays and to measurably affect Earth's atmosphere. At 5,000 light-years, 1/10 the distance, the energy flux would have been 100 times higher. The atmospheric effects would have been correspondingly more severe. At 500 light-years, the energy flux would be 10,000 times higher than what Earth experienced. This is still far beyond the danger threshold for ozone destruction. A flare of this intensity at this distance would strip away the ozone layer within hours. The surface of the planet would be bathed in ultraviolet radiation at levels lethal to most surface life. At 50 light-years, the flux would be 1,000,000 times higher. At this distance, the direct radiation itself would be dangerous. Organisms on the daylight side of the planet would receive radiation doses comparable to standing near a nuclear explosion. The atmosphere would be ionized to unprecedented levels. Electronics would be destroyed. The fabric of technological civilization would be torn apart in a fraction of a second. At 5 light-years, we enter the realm where the radiation would be directly lethal, even to protected life. The energy deposited in the atmosphere would be sufficient to strip away significant portions of it. The surface temperature would spike from the absorbed radiation. Mass extinction would be certain. These scenarios are hypothetical, but they are grounded in physics. The inverse square law is unforgiving. Distance is our only protection from these cosmic events, and distance is determined entirely by the random distribution of magnetars throughout the galaxy. The story of our understanding of magnetars is, in many ways, a story about the limits of scientific imagination. When Duncan and Thompson first proposed these objects in 1992, the idea seemed almost absurd. Magnetic fields 1,000 times stronger than any neutron star previously observed. Objects so violent that they could release more energy in a fraction of a second than the sun produces in 100,000 years. Most astronomers dismiss the concept, but the universe does not care what we consider plausible. It operates according to its own rules, creating phenomena that exceed our expectations and challenge our theories. The magnetar was waiting to be discovered, whether or not scientists believed it could exist. This is a pattern in astronomy. The universe repeatedly surprises us with objects and events more extreme than we predicted. Black holes were once considered mathematical curiosities. Gamma ray bursts were so bright that early observers assumed they must be coming from nearby objects, not from billions of light years away. Neutron stars themselves were theoretical speculation for decades before pulsars were discovered. Each time, the universe proved to be stranger and more violent than we imagined. Magnetars continue this tradition. They represent matter and energy behaving in ways that test the boundaries of our physical theories. They produce radiation that affects worlds tens of thousands of light years away. They connect to other cosmic mysteries, from fast radio bursts to the most powerful explosions in the universe, and they remind us that the cosmos is not a gentle place. We share our galaxy with monsters. Most of them are far away. Most of them will never affect us. Most of the time, we can look up at the night sky and feel only wonder at its beauty, without thinking about the violence that lurks behind the quiet light of distant stars. But once in a while, on an otherwise ordinary night in December, the cosmos reaches out and reminds us. A star died tens of thousands of years ago, leaving behind a corpse no bigger than a city. spinning in the darkness with a magnetic field that defies comprehension. And on that corpse, the strongest material in the universe cracked under pressures that no earthly substance could withstand. The resulting scream of gamma rays traveled across the galaxy at the speed of light, washing over everything in its path. It blinded satellites. It compressed magnetic fields. It ionized atmospheres. It left permanent marks on worlds that happened to lie in its path. Earth was one of those worlds. We survived because we were far enough away. The next time, if there is a next time from a closer source, we might not be so fortunate. The Magnetar does not know we exist. It does not care. It simply is a product of stellar evolution, a consequence of physics, an object that sits at the boundary of what matter can do and still remain matter. And somewhere in the galaxy, right now, another Magnetar is accumulating stress in its crust. The magnetic field lines are twisting. The pressure is building. The strongest material in the universe is straining toward its breaking point. We cannot know when it will crack. We cannot know where the next burst will originate. We can only look up at the stars and appreciate that the universe, for all its beauty, harbors phenomena of terrifying power. We are very small. The universe is very large. And somewhere out there, among the hundreds of billions of stars in our galaxy, a Magnetar is waiting to crack. When it does, we can only hope we are not in its path. There is one final thought worth considering as we contemplate these cosmic monsters. The December 2004 event happened during the day in the United States, invisible to naked eye observers. The gamma rays that washed over our planet could not be seen or felt by any human being without instruments. We went about our lives, unaware that a dead star on the other side of the galaxy had just touched our world. This invisibility is both reassuring and unsettling. Reassuring because the universe's violence does not intrude on our daily experience. Unsettling because it reminds us how much happens beyond our awareness, how many cosmic events shape our world without our knowledge or consent. The ancients looked up at the sky and saw order, regularity, the eternal dance of stars following predictable paths. They could not have imagined the violence hidden behind that serene beauty. They could not have conceived of objects that packed the mass of the sun into a sphere the size of Manhattan, or magnetic fields that reshape the very vacuum of space. We now know better. We know the universe is not the calm, orderly place our ancestors imagined. It is a vast arena of unimaginable energies and terrifying phenomena, punctuated by explosions that make our largest nuclear weapons seem like fireflies in comparison. And yet, we are here. Life has persisted on this planet for nearly 4 billion years, surviving ice ages and asteroid impacts, volcanic winters and climate shifts. Perhaps we have been lucky, avoiding the worst cosmic hazards by simple chance. Perhaps the universe is not quite as dangerous as the statistics suggest. Or perhaps the resilience of life is greater than we realize. Whatever the case, the Magnetar reminds us of our place in the cosmic order. We are small creatures on a small world, orbiting an unremarkable star in a galaxy that contains hundreds of billions of others. We have no special protection from the universe's violence, no cosmic guardian watching over our fragile biosphere. What we have is knowledge. We have instruments that can detect gamma rays from across the galaxy. We have theories that predict how Magnetars behave. We have scientists who dedicate their careers to understanding these phenomena. That knowledge is our only defense, such as it is. Not a shield against the radiation that might someday arrive from a nearby magnetar, but an awareness of the dangers we face and the universe we inhabit. The magnetar does not care whether we understand it, but perhaps in understanding it, we gain something valuable, a clearer vision of reality, stripped of comfortable illusions, grounded in the actual physics of stars and matter and energy. That vision is sometimes terrifying. The universe is not safe, but it is magnificent. And the magnetar, for all its dangers, is one of its most magnificent creations. Somewhere out there, in the darkness between the stars, the most powerful magnets in the universe spin silently, waiting. Their next eruption might come tomorrow, or 1,000 years from now, or never at all. We cannot know. We can only watch and wonder and appreciate with humility and awe the strange and violent cosmos we call home.